Thousands of miles out in the Pacific, the image of a thermonuclear explosion is etched forever on film. Thousands of miles out in the Pacific, the image of a thermonuclear explosion is etched forever on film. Thousands of miles out in the Pacific, the image of a thermonuclear explosion is etched forever on film. From Alaska to Asia, in any one of 1,000 different places throughout the world, whenever, wherever a significant Air Force event occurs, an Air Force cameraman is on the scene, documenting for posterity history in the making. Another spot on the globe where history is being made almost daily is here at Edwards Air Force Base near Lancaster, California, proving ground for tomorrow's manned air and aerospace vehicles. This center is among 6 doing specialized experimental work under the Air Force Systems Command. Its mission is developing the nation's newest space weapons systems. Hangars, shops, and runways provide facilities for approximately 10,000 military and Air Force civilian technicians, as well as prime Air Force contractors engaged in Air Force Systems Command research and development activities. Rogers Dry Lake provides the world's finest natural landing field for emergencies and recovery of test aircraft, such as the combined Air Force, Navy, and NASA X-15 manned research vehicle. The photography branch at Edwards Air Force Base maintains a highly specialized group of optical instrumentation engineers, cameramen, photographers, laboratory technicians, and essential operations personnel. Their job is to record on film events which the human eye is incapable of perceiving except in the form of slow-motion pictures. In addition, the photography branch provides photographic documentation for the United States Air Force for historical purposes, for use in training films, newsreel television, as well as footage for use in commercial productions. Here are working group conferences and sessions. These men are being briefed on all aspects of a test to be documented in the air and on the ground. Each photographic supervisor learns the part his particular photo team will play in the operation. At the same time, cameras and associated equipment are made ready for the test event. The camera section is, of course, completely equipped for any type of still or motion picture assignment. Equipment includes standard and high-speed motion picture cameras, capable of shooting as many as 8,000 pictures a second. Assignments vary from a simple newsreel series to a complicated motion picture production for engineering and staff film reports. Aerial motion picture cameramen play an important part in documenting air-to-air sequences of aircraft test vehicles in flight. These highly qualified cameramen are experienced in the art of airborne photography at supersonic speeds. They fly high, recording significant air sequences of flight testing, like the release of the X-15 from its mothership, the B-52. Or the U-2 with its gull-like wings. The F-104 Starfighter. Or a flight of the latest supersonic jet trainers like the T-38 Talon. Yes, they're a high-flying bunch, ready and able to cover any emergency. And emergencies receive top photographic coverage at Edwards. The failure of a landing gear and tires on a Strategic Air Command B-58 required the combined teamwork of engineers, pilots, crash and firefighting personnel, and airborne cameramen to document a technique devised at Edwards Air Force Base to save valuable aircraft in such an emergency. Film stories like this are used by SAC to train their bomber crews in the best procedures to follow in aircraft emergencies. A fully equipped motion picture and still photographic laboratory supports the photographic effort at Edwards. In the motion picture processing section, there are two color machines, the Fonda 35mm or 16mm, and the 16mm Technicolor design machine, which process approximately 220,000 feet of color film per month. Also, two black and white 16mm and 35mm Houston machines process approximately 190,000 feet of black and white each month. The motion picture printing capability covers every phase, from the Acme optical printer to the 16mm and 35mm Bell & Howell Model D and J printers using color or black and white film. This fully equipped motion picture printing facility serves not only its own production requirements, but it also serves the needs of project officers and engineers in printing of their instrumentation and engineering films. An average output per year for the printers runs at approximately 1,500,000 feet. Once motion picture coverage of an event is accomplished and lab processing completed, the film is turned over to one of the several film editors. His job is to review the film, break it down into its essential sequences, and then put the pieces back together in a continuity to meet the requirement of either a staff film report, a training aid, or perhaps a briefing film. But motion pictures are not the only photographic products of the laboratory. There are still photographers and hyposplashers in a completely equipped still laboratory. They provide various types of services, ranging from copying to engineering stills in color and black and white, and the normal information and news photography. Production in this unit averages about 20,000 prints of all types per month, including 35mm color slides and various color dye transfer prints and transparencies. A typical example is the 70mm color sequence of an X-15 landing. Some 30 miles from the main photographic laboratory, a detachment is maintained on Lumen Ridge to provide photographic support to the Rocket Research Laboratory, Air Force Systems Command. This detachment has the responsibility for producing documentary, engineering, and scientific photography in both motion picture and stills of highly specialized Air Force and contractor original research and development work on rocket propulsion systems, liquid and solid propellant, and evaluation tests of captive missiles. Typical of the photographic service provided by this detachment are these technical cameramen who are preparing remotely operated cameras, installed in protective camera shelters in close proximity to the test vehicle. These camera stations will record ignition phases, flame patterns, quick disconnect systems, and predetermined explosions. These men are responsible for the installation, loading, calibration, and operation of highly specialized cameras designed for high-speed motion analysis in still and motion pictures of each test series. Individual cameras may occasionally malfunction at a critical period in the long countdown. Usually, it can be corrected in time. Last-minute final checks are made. Everything is now ready for the test. Camera equipment and electronic components are usually checked out. Yet, as long as there are cool, calm, and collected individuals like this technical cameraman, little trouble is expected from malfunctions. But it's a close shave trying to beat the red light and the warning siren. By the time the final seconds of the terminal countdown begins, the camera console operator throws the switches that start the surveillance cameras. And at -5 seconds, all super high-speed motion picture cameras and 70mm Hulchers are turned on. Now let's take a position below the ridge and observe a typical rocket test firing. Not all such tests are as successful as the one just witnessed. There are failures. When a space booster engine destroys itself on the test stand, the reason for its failure is usually consumed in the flames of the explosion. Recovery of such film is not always as easy as it appears here. It does, however, convey the point that by careful study and analysis of the film recovered, the engineers can usually determine the cause of the failure, and such evaluation usually prevents its recurrence. A second detachment of the photography branch is assigned to the experimental high-speed track. Its mission is to collect photographic instrumentation data of all tests conducted on the track. The track is 20,000 feet long and utilizes rocket-propelled sleds to simulate aircraft speeds on the ground. This permits documentation of components being tested under controlled conditions. The track is extremely versatile when used for full-scale tests, such as the blast effects experiment as seen here. High-speed track optical instrumentation does not compete with other instrumentation methods except in very restricted areas. The effort here is to provide the test engineer with optical data in order that he can better evaluate the results of his tests. Spaced at accurate intervals on a line parallel to the track are the primary metric cameras. 35 millimeters, operating from 1,000 to 2,000 frames a second. The 16 millimeters and 70 millimeters running at speeds up to 4,000 frames per second. Various other types of cameras are also used, some mounted between the rails. Dual-mounted manual tracking cameras complete a portion of high-speed track documentation activities. Let's take a look at the end product from some of these camera positions. Manual hand tracking at 200 frames per second, B-70 capsule ejection test. Fixed camera, low angle on sled, 1,000 frames a second seat ejection test. Ballistic missile impact test at 2,000 frames a second. Static seat ejection through plexiglass canopy, filmed at 1,000 frames a second. Not all tests are conducted on the high-speed track. For instance, this seat ejection was made from a static mock-up to a closed aircraft canopy to determine the feasibility of air crews safely ejecting in this manner. The photography branch supplies processing support to the space positioning branch at Edwards. This unit tracks and accurately positions test aircraft by radar and cameras equipped with special telephoto lenses. An example of the photo product is this T-38 Talon supersonic trainer undergoing spin tests. The ultimate in the space positioning optical equipment is this highly sensitive satellite tracking instrument, the Baker Nun. In the meantime, the men and the women at the photographic laboratory will continue to process negatives, edit documentary and engineering films, turn out reams of still prints, file more cans of film for posterity, schedule and coordinate more projects, while the cameramen manufacture more optical records, or conduct research with new photo techniques like fiber optics, which make it possible to shoot around corners. Shown here is a 12.5-foot oriented fiber bundle connected to the camera, while the taking lens is on the opposite end of the fiber bundle, close to the subject. The image seen here is being transmitted through the fiber optics oriented bundle 12.5 feet to the film plane. The black dots appearing on the screen are the result of damaged fibers, yet the picture may still be clearly distinguished. This drawing illustrates the unique application of fiber optics in studying the small, minute bubbles that have clung to the bottom of a fuel sensor inside an Atlas missile during fueling operations. You have seen only a small part of the photographic efforts being carried on at Edwards Air Force Base. With each coming day, with each new test, Air Force cameramen will be on the job documenting the performance of new weapons, new aircraft, new space vehicle boosters, new techniques, supporting, as in the past, those things which will lead ultimately to man's conquest of the last frontier, to space and beyond.